Hello, everyone. My name is Binyi. I'm a postdoc researcher at Stanford, and today I'll present LatticeFold, which is a new folding scheme that has wide applications, including zkVM. This is a joint work with our unique Dan. Okay, so the talk today is about building a magic primitive called zk-snarks. What is zk-snark? Roughly, it's a primitive that allows you to convince the verifier that certain computations were done correctly. And usually this computation involves a public instance part and a secret witness. For example, you can use it to prove that you know the pre-image of some public hash, or you can use it to prove that you know the secret key of some public Ethereum address, so you are the earner. And you can do more than that. You can prove arbitrary NP relation. So in snark scheme, initially, given some NP relation represented as an arithmetic circuit C here, you will run some setup algorithm to generate some parameters for prover and verifier. Then the prover, whenever he gets a statement that he wants to prove, will run this proving algorithm to generate short proof. And then the verifier will check this proof against public instance part of these statements. And if it's valid, then she'll be convinced that the statement is true and prover knows the witness. Beyond typical property like completeness, soundness, knowledge soundness, or zero knowledge, there's one unique feature of snark that makes it so useful, called succinctness. That means even if this arithmetic circuit is so expensive to evaluate, this proof should still remain really short and very cheap to verify. This kind of asymmetry makes it very useful in many applications, including scaling blockchain. So in a traditional blockchain, there are many blockchain nodes that will maintain some global blockchain state. And in each round, after some consensus algorithm, they will agree upon a block transactions to be executed later. And then now everyone needs to execute it and run the computation and obtain the global blockchain state. That definitely leads to a lot of redundant computation and execution, which makes blockchain less scalable and performant. However, suppose we have a really, really efficient zk-snark. Let's see what can happen. At a very high level, the idea is to let the prover to do the execution and attach and publish a snark proof validating the correctness of this execution, and then everyone will receive this proof and the claimed update states. And now everyone only needs to verify this proof instead of rerunning the computation. And because of succinctness, verifying proof is much, much cheaper than rerunning computation, and this saves a lot of computations and also makes blockchain more scalable. But this raises a different question in that how does a prover who possibly use commodity laptop or desktop or server, how can it generate this proof really, really efficiently? The dream goal here, of course, is proving as fast as compute. But that's actually a challenging problem for which that there are a lot of companies trying to work on it. So to illustrate the issue here, let's consider a typical approach to solving this. The idea is to model this VM execution as a fixed arithmetic circuit that you should fix beforehand. So that means the number of transactions you can handle should also be fixed before you receive the block. Then in the online time, when the prover receives this online block of transactions, then he will execute this block of transactions to obtain the execution trace and transform it into the witness of these arithmetic circuits. And after that, after getting the entire witness, then he can pick his favorite snark algorithm like Stark or Plonk to generate the final proof. However, this framework has several limitations, mainly because that in these particular applications, this circuit can be gigantic for simulating, say, millions or even billions of instructions, because this block can be large in order to get really, really good scalability. And that means even generating this witness can be a bottleneck, can be really computationally intensive. And remember, you can't even start doing the proving unless you get entire witness. And second, moreover, the snark algorithm itself can also be more memory and computationally intensive to compute when the disproving instance becomes really gigantic, like billions of size or even tens of billion size, because it uses some algorithm like FFTs or multi-group exponentiations that is less memory efficient or computationally efficient when the instance size is really, really, really large. And finally, as I mentioned before, the circuit has to be fixed beforehand. So we really can't say that suppose in online time you receive no matter whether you receive a really small block or really large block, you always have to pay the worst case scenario proving cost. So that's also bad. So given this, there's an alternative way to build a ZK-VM proof using the so-called incrementally verifiable computation. And at a very high level, the idea to split this execution of blocks of transactions into many, many small pieces or many, many iterative steps. And then in each iterative step, the prover will generate a snark proof for these particular statements, which checks two things. First, that the state transition at this particular step is done correctly. And second, he also needs to check that exists some good proof that validates the correctness of all the previous steps. And how to check it, you just run this snark verify inside this statement circuit. And suppose now you get a new proof that validates correctness of these new statements, then now this new proof can serve as a certificate validating the correctness for all the previous executions, including this particular step. And you can do this again and again, and finally the last proof will be able to validate the correctness of entire ZK-VM execution. The advantage of this kind of framework is that you can now pipeline the proving and the witness generation process. That means you only need to know a little bit about the entire witness in order to run the first several iterative proving process. And that's much better than before, where you have to get the entire witness first. And second, because each iterative statement now only needs to embed a single state transition or very few number of state transitions, the statements here that you want to prove can also be much smaller, so that the snark algorithm you run will also need less memory. Finally, if you use some other more sophisticated way to do recursion called proof carrying data, this can actually also be made very, very parallelization friendly. However, it also has trade-off and limitations. The limitations here is that you have to pay some extra cost for generating such a proof. That is, you have to prove some statements about snark verification, which is not existent before in this monolithic snark framework. And in practice, this is actually concretely expensive for simulating those pairing operations or group expansions or many Merkle path openings. So that's concretely not that efficient until very recently. And so the question is whether we can have an alternative way to build an IVC or PCD. The answer is definitely yes, and this was actually answered by other researchers like several years ago. Around 2020 and 2021, there are two research groups figured out that actually we can build an IVC or PCD without relying on snark, but purely from a weaker primitive called folding schemes, which makes use of another crypto primitive, which I would call homomorphic binding commitment. So let me start with recall what a homomorphic commitment is. So a commitment allows you to compress a really long message into a short string that's bound to this message, meaning that if you fix this commitment, it's hard for you to open in two different messages. And second, it needs to satisfy this homomorphic property, meaning that the commitment to, for example, the addition of two messages is basically just the addition of the corresponding commitments to the separate messages. And this homomorphic property is quite useful because whenever you want to check some linear relation over this long and expensive message space, it suffices for you to just check the corresponding relations over the commitment space, which is usually much cheaper and simpler. And this is also the core insight on how to build an efficient folding scheme, which I now am ready to explain what it is. So intuitively, it very roughly is a primitive that allows you to compress multiple MP statements into a single one. Okay? Why is it useful? Suppose you want to prove, like I know the pre-image of many, many hashes, and you want to have a separate proof for each of them. That's usually pretty like communication inefficient and less efficient. And instead, suppose you have folding scheme, you can compress multiple MP statements first into a single same-size folding statement and just generate a single proof of that, which is usually more efficient. Okay, now let me be a little bit more specific. Let RMP be some MP complete relation. In a folding scheme, usually what we do is that we will insert a homomorphic commitment to the witness inside the public instance and give you a committed MP relation, which further checks that this is the correct commitment to the witness. And now a folding scheme syntactically allows you to merge two instances with pair inside this relation. Actually, should be a relaxed relation, but now I will omit technicality here. You merge these two instances with pair in this relation into a new folded instance with pair in the same relation. And we will also output proof pi here that allows the verifier later to efficiently check that this folded instance is honestly derived from the two input instances. And the one thing to note here is that folding verifier does not have access to this long witness here. So usually they are very, very efficient. And it also needs to satisfy similar completeness and North-South property that's very similar to snark. But the key point here, the greatness about folding scheme here is that usually we have very, very efficient instantiation of folding scheme compared to those snark counterparts. For example, the folding proof is pretty much just the randomly combination of two witness vectors, which are which consist of field elements. And the folding verifier is even simpler, it's just a linear combination of two corresponding commitments, which is very, very simple compared to snark that, for example, you need to use pairing or something. So this is good, and even better, it was shown that we can actually construct IVC purely from folding scheme. And the idea is very similar to the previous recursive snark idea. Well, at each iterative steps, the folding prover will collect the two statements he got previously, which is one online statement in the previous step, and another one is accumulated statement that collect or merge all the statements that has been done before that. And then in this step, he'll fold these two statements into new accumulated statements that checks that, basically checking that all the statements were checking correctly before. And then in this step, he also generates a new online statement checking that state transition at this particular step is done correctly. But of course, you also need to check that the folding was done correctly. And how to check that? You run the folding verifier here. And then you get a new online statement for which in the next step you can fold again. And finally, you'll get a last folded statement, and IVC verifier will check this last folded statements. And if it's true, that implies all the DKVM execution was done correctly. The logic is very similar to recursive snark. The nice thing here about IVC from folding is that in each iterative step, we can instantiate in a much, much faster way. Why? Because you can see here, we have replaced this snark proving algorithm with this folding prover, which is much faster. And on the other hand, this recursive statement or this statement we want to fold is also much, much cheaper because we have replaced this snark verification gadget with this folding verification gadget, which is much smaller. So given this, I hope I convinced you that IVC from folding is very efficient. And this reduces to the next question on how to build a very efficient folding scheme. And the first question we need to answer here is, which kind of homomorphic commitment should we use inside it? And one typical way and approach is to use Peterson commitments, which is exactly the thing that used in the previous works. And in Peterson commitment schemes, the message is a message vector of length n, which consists of many scalar field elements. And the commitment is a multi-group exponentiation between this message and a vector of random-based generators. And this is a group elements, or it can be represented as a elliptic curve point, represented as two base field elements over FQ. The thing here is that both FP and FQ is very, very large. And this is inherent because of the assumption that this relies on called discrete log, which needs this to be large in order to be secure. And however, this is, it has some efficiency issues here in the sense that when you do the committing, it has to perform a lot of expensive group exponentiations over this large field, which is quite expensive, which I think also the last talk, Ellie talked about this, that we should focus on small field arithmetics. And if you instantiate it and obtain the folding scheme with it, the folding verifier circuit now will consist of a few group exponentiation done over the base field and some hash and field operation done over the scalar field. That means this circuit needs to represent and support both FP and FQ operations. So unavoidably, you have to do some so-called field emulation. Means that those FP operations needs to be represented as arithmetic over FQ, and because you only have a circuit over FQ, or vice versa. But anyway, this kind of translation is also very, very expensive. Finally, this scheme is also vulnerable to quantum attack because of this famous Shor's algorithm that can break discrete log. Given this, we choose to use a different commitments called lattice-based commitments, and we introduce the first folding scheme called LatticeFold from these commitments. It has several nice features here. First, now it supports the use of really fast and small field arithmetics. For example, you can use 64-bit prime fields or 32-bit prime fields. And second, because the commitment scheme will have a really nice property here, where the message space and commitment space, they all lie in the same kind of algebra object called a polynomial ring. So everything is done over the same field or same ring. There's no need to do non-native field emulation anymore in the folding verified circuit. And this also makes the circuit concretely more efficient. And finally, this commitment schemes is based on this some lattice assumption that's believed to be quantum attack resistant. So we also obtain a plausibly post-quantum secure schemes. And finally, supports the use of some high-degree constraint system, which is very convenient to use in practice for represent complex computation using really efficient and succinct circuits. Okay, so that's our main result. And now let me start by reviewing these commitments we use called R-type binding commitments. Again, recall our goal is to compress a long message into a short string. And here, this short string is basically just the lambda ZQ elements, where lambda is some parameter related to security parameter, and Q is some small primes. And we do this by multiplying this message vector with some pseudo-randomly generated matrix A here, which is a matrix over ZQ that has dimension lambda by n. But you might notice here, we have very strange requirements here for the message space. Well, for every element of this vector, we have to make sure that it's always inside this really narrow range of minus beta and beta. Well, beta is these range-bound parameters. And turns out this is actually essential for obtaining the binding property from this lattice assumption. So it is really necessary to have that requirement. And beyond that, we also satisfy this homomorphic property given the linearity of matrix multiplication, which is pretty straightforward. However, again, you have to be careful because you always have to make sure that after these linear operations, this resulting integer vector should still be inside this message space of the commitment scheme. Otherwise, this commitment is no longer well defined. Okay, so at this point, the committing complexity is still not very efficient. It takes like lambda times n small field operations. But we can do much better by using a variant of it. And here we'll introduce a new object called polynomial rings, or RQ. Roughly is the set of polynomials that has degree less than d and with ZQ coefficients and modulo some polynomial like x to the d plus 1. And now the idea here is very simple and it's very similar to before. Well, the only change here is that we'll view this previous scheme in a slightly different way. The idea is that we'll view every vector of DZQ elements just as the coefficients of some single polynomial ring elements. And that will translate to this. Well, W becomes W tilde, IA becomes L tilde, and CW becomes CW tilde. And now the key difference here is that when we commit, instead of performing matrix multiplication over ZQ, we just make matrix multiplication over RQ. And because we have a really efficient polynomial multiplication algorithm using NTT, this actually leads to much more efficient algorithms. For example, if you set this degree d to be exactly lambda, then L tilde basically now just a vector of n by d, and it's just an inner product. And that's the inner product is just n by d ring operations, and that will translate to approximately n log lambda small field operations, which is very efficient and also parallelization friendly. A great thing here is that actually there are many software and hardware optimizations for it in the fully homomorphic encryption setting and lattice signature scenarios, which makes it actually blazingly fast. Okay, so now I'm ready to go back to our main task for constructing a folding scheme from R-type commitments. For simplicity, I'll consider an even simpler problem. Well, the public instance only consists of these homomorphic commitments. And our goal here now is to merge these two commitment witness pairs into a single one. And The naive idea is to do random linear combination, which is exactly the way that has been used in all the previous existing works. However, in this scenario, we immediately runs into trouble because after folding, this folded witness will no longer be inside the message space of the commitments. And that's a big issue. And it's not an issue only because this random scalar is large, so that the norm will blow up. It's still an issue even if you just add the two witnesses together, because it's possible that initially those two witnesses might already approach the edge of this narrow space, and if you add them, it's very easy to go outside. And if you go outside, then it's bad, because the binding property no longer holds, and actually folding scheme will also no longer be secure. And we have some concrete attacks for that. So we face a real challenge here in that how can we keep this folded witness always stay in this bounded message space of commitments, even after so many folding steps. And this is essential for the security of folding scheme. We solved this issue using two techniques. The first technique is called decomposition trick, but put it another way, another understanding of it is to try to re-represent and think about this input witness in a slightly different way. So let me be more specific and explain what decomposition works. Say you have a single integer that's inside this range of minus beta and beta, and our idea is to run some algorithm, some deterministic algorithm that's very similar to a bit decomposition algorithm to split its multiple integers that now have even smaller range. And these multiple integers here, a1 to ak, they are also can be understood as a different representation of a here, right? The binary representation, for example. And the great thing here is that every integer now is having even lower norms. And actually, we can extend this idea to the ring case or polynomial ring case. Well, what we do is just we split the coefficients separately using these algorithms. And now let's see why it's useful for us to do folding. Suppose we have two input witness pairs initially, and then we run this deterministic algorithm to split them up into, say, for example, 4 instances with pair, where each intermediate instance with pair now is even in an even lower range, basically minus b and b here. And at this point, now it suddenly, magically, now we can do random combination. But you need to be a little bit careful in that these random challenges still needs to be inside, have very small coefficients. And with that, with some careful choice of parameters, finally, you can guarantee that after folding, the folded witness will always be inside this massive space of commitments, because b is smaller than beta. Even if you have some blow up, you can control it to be inside this beta. But this solves our previous issue, but this raises a different question, however. And another issue here is, remember, the verifier also need to check that prover is not cheating, right? What if prover is using some bad intermediate witness that's slightly larger than minus b and b and still pass the check? Also, we need to make sure this folding verifier is efficient, so we cannot afford to send all this intermediate witness to verifier and let it to check it, because it's very expensive. So that means we really need a folding prover to convince the verifier using a range proof to check, to convince the verifier that indeed I'm not cheating, I'm indeed using low norm witness in this intermediate step. And we achieve this by introducing a new novel range proof techniques from the sum check techniques. And for time reason, I won't dig really deep into these technical details, but the key point here is that both the proving time and the verifier complexity is very efficient. The proof time is linear, and the verifier complexity is still logarithmic. Okay, so finally, I want to highlight the concrete efficiency of this scheme a little bit and compare to the state of the art. Also, we know that recently after we published this paper, there's a concurrent work which built a folding scheme purely from hashing, which is also a very elegant scheme, and they also have really efficient prover. And for LatticeFold, our prover is also very efficient. It's approximately just a linear number of small field operations, which is much better than Peterson-based scheme that involves a lot of multi-group exponentiations over really large fields. And in terms of verifier circuit, it's also very competitive. The dominant cause is some sum checker verifier that takes logarithmic number of hashes. And the one thing to note here is that we don't need hash to be fast outside the circuit. we can use arbitrary snark-friendly hash because in our schemes, the prover doesn't perform too many hash operations. So concretely, we can make the verified circuit very, very efficient compared to hash-based folding schemes. And it's also competitive to these Peterson-based schemes because we have fully eliminated the non-native field emulations. Finally, I want to mention two advantages of using LatticeFold over this hash-based folding scheme. The first is that LatticeFold allows you to fold for an unbounded constant number of steps. Well, in hash-based folding scheme, you have to fix some constant beforehand, and if you fold for more than that number of steps, there will be a concrete attack that breaks the security of the scheme. And finally, suppose you are using some applications that involve some sparse witness, meaning that the number of non-zero entries is really small, which is the case for some non-uniform computation or branch program executions. Then it's really advantageous to use LatticeFold because the committing complexity is only proportional to the number of non-zero entries, and you don't need to do anything about those zero entries, which is not the case for the hash-based proofing system because it needs to perform some Merkle tree commitments that is always the same cost no matter whether it's zero or not. Okay, so I think that's all I want to cover. And in summary, we have introduced LatticeFold, which is the first lattice-based folding scheme that supports really fast and small field arithmetics, have efficient verified circuit because it eliminates non-native field emulations, and it is also plausibly quantum secure. We also want to highlight that in our recent updated version of the paper, we have introduced another optimized folding scheme for high-degree constraint systems that is like now almost 50% more efficient than the previous one. And now there's only one subchecks, and both the prover time and the verified complexity are also significantly improved. Okay, so that's it. And basically, I want to mention a little bit about open problem here. There are many, but I only will mention a few of them. The first low-hanging fruits, I think, here is to integrate it with Lasso to support table lookups, which I think won't to be too hard. However, an even long-term and more ambitious goal is to check whether we can actually remove the use of this witness decomposition or range proof checks that might even further improve the efficiency of LatticeFold and kind of approaching our dream goal of proving as fast as compute. Okay, that's it, and thank you so much.
Terrific. Thanks for the wonderful talk. And we have a little bit of time for questions. Yeah, Aline, go ahead.
Hey, thanks for the talk. Really complicated math. Could only follow a little bit of it, but I saw that you mentioned some check-based range proofs. And this was something I once thought about and wondered if we could get a more efficiently batchable range proof from some check. Does your range proof have nice batching properties?
Yes. Yes, exactly. One of the great features of our range proofs is exactly very good for batching. For example, here you have multiple instances with pairs, right? You have to approve the range for each of them. And actually, you only need to run one single sum check for all of them. So it's really good for batching.
And I suppose your range proof is for iTie hashes, but it could probably be generalized to Peterson commitments, no?
Yes, I think so. And I think at some follow-up work, there are indeed some paper that try to do range proofs for Peterson-based commitments. So I think this should be extendable. Yeah.
Cool. Yeah, would love to talk to you about it. Thanks.
Yeah. Thank you.
Great. Any other questions? All right. In that case, let's thank Binyi one more time. Thank you.